Hello world, it's Siraj, and today we're going to talk about pose estimation using Tensorflow.js. What you're seeing behind me is a demo of real-time pose estimation using Tensorflow.js. What it's doing is it's estimating what all my body part poses are. If I go back a little bit, it's going to show like all these little things, Okay, so you see a little bit of that. I'm going to go back out of that. So that's the demo for today's video, and we're going to do this using Tensorflow.js. This is really simple to do in the browser. Anybody can do it. You don't need to install any dependencies. You don't need to make any kind of configurations. You don't need to download anything. That's the great thing about JavaScript, is that it's so simple to use. And because TensorFlow has now been ported to the browser, pretty much anybody can make incredible machine learning applications that anybody can access, because pretty much any computing device has JavaScript enabled for browser access, right? So that's what we're going to do today. I'm going to talk a little bit about Tensorflow.js, and then we're going to go into the code, how pose estimation works architecturally, programmatically, et cetera, et cetera. Okay, so right, ML used to require lots of time and money to get started. You had to build your own, deep learning rig, buy your own GPUs, install all this stuff, configurations, CUDA, drivers, this, that. It was a huge headache. And since then, the whole field has kind of went into this period of ease of use. Everything's being democratized. Everything's getting easier for anybody, which is awesome. And I think that Tensorflow.js is a good example of that being magnified into the eye of the public. But really, there are 3 points that I particularly find very interesting about Tensorflow.js, and in general, machine learning happening in the browser, why I think it's a good thing. So the first reason is privacy, right? So privacy is a big issue if you're a healthcare company, if you are if you have any kind of critical data that you don't want people to know about, privacy is crucial. So ideally, you could train your model at the edge instead of on the cloud. That means on your device instead of on someone else's device. And if you can do that, you can keep the data local. You don't have to send it anywhere, which is awesome. The second reason is wider distribution. Like I said, pretty much any computing device, phone, laptop, tablet has JavaScript enabled, whether it's through a browser, whether it's through, whatever, they have JavaScript enabled. So you'll reach the widest audience. The third point is distributed computing. So if we can leverage client-side data from many users to train a model in real time, I think this is particularly exciting. If you think about it, you have a web app and you deploy it to a bunch of people. You can train it on their data in real time and make your model as a whole better, which is awesome, right? So Uber and Waymo and all these companies, they're doing that for their self-driving cars. Like they're learning in real time, and then those learnings are being transferred to a global model. And now we can do this for anything really, not just for self-driving cars, but for simple web apps, classification, inference for all sorts of things, game playing, predictive analytics for marketing companies and finance, stock prices, things like that. Numerai is doing that in some way. But anyway, there's a lot of potential there. And I have a video on Tensorflow.js. So just search Tensorflow.js Siraj on YouTube and you'll find it. But I just want to go over like one simple part of it. So we have just this image right here. So WebGL is how graphics are computed in the browser right now. It's a low-level library for that. And so on top of WebGL is the browser. And what you see on the right is soon, because it's talking about TPUs, right? So ideally you could train this thing on TPUs, but we don't really have that yet in our machines. We have GPUs and CPUs, but you can train Tensorflow.js on CPUs and GPUs. It doesn't matter. So on top of the browser, you have the Ops API. And the Ops API is just like TensorFlow, right? You've got variables, constants. It's basically long code. It's detailed code of how you define your computation graph, what it looks like, what the variables are, what the parameters are, what the learning rate is, what all those hyperparameters are. You can do it in detail. Or you can use the layers API, which is basically Keras, one line per layer. You can do in 9 lines what you would otherwise do in like 100 lines. Which is what the layers API is. So that's kind of high level of what it looks like. If you want to do something simple, use the layers API. If you want to get detailed and make sure your model is state of the art, use the Ops API. And the pipeline is actually very simple. So what I've seen on GitHub in terms of developer activity is a lot of developers are using pre-trained models because it's so easy to use, right? So transfer learning, I think, is going to be a huge use case. It already is a huge use case for Tensorflow.js. You can use a pre-trained model, AlexNet, MobileNet, VGGNet, GoogleNet. There's a million pre-trained models that were trained on different sets of images, on games, on human interactions, etc. Take one of those pre-trained models and you can use it in the browser easily with like a few lines of code. So the pipeline is a 3-step process. The first part is to load a model, right? So in order to do that, we need 2 components. We need the model file and we need the weights manifest, right? So where to find the weights and what the architecture of your model is, right? How many layers do you have? What are the hyperparameters? And the weights, what is it learned? And once you have those 2 things, boom, you have a pre-trained network that you can run in the browser. Programmatically speaking, this is very simple, right? So we can load up a frozen model from wherever we have. We can create constants for where our weights are, where our model is. What do we want to name our input node? What do we want to name our output node? And then we can load our frozen model just like this, using the model URL. Remember those two components. That's all we need. The rest of the code you see here is just like for naming purposes. But this last line, including these 2 parameters, are all you need in a single line. That's it, to load up a model that's already been trained. And this could have been trained in TensorFlow Python. It could be trained in TensorFlow C++, but you can import it into Tensorflow.js very easily. The second step is pre-processing. So a neural network has a specific input definition. You can't just input any kind of data. It's got to be in the right format, right? You can't input an 18-dimensional vector into a 3-dimensional neural network, right? So if its weight values are assuming a certain dimension size, you can't just say, oh, it's going to be this dimension size and just force it in. It doesn't work like that. So you have to do some pre-processing in order to do that. So to do that, first we'll convert pixels to Tensorflow.js's input tensor. So we have some source, and the source is that the source of what we're training on. And then what we can do is we can say, okay, let's take the input, and then from pixels, the source is that the data that we're training on. We'll convert it into pixels just like that. So that's our first step. So now it's in this pixelated format that's appropriate for Tensorflow.js. Then we'll crop the input. So if we want to use part of the image, so we'll say, where's the mobilenet.crop image input? And that's that pixelated version, so we cropped it. And lastly, we'll set the batch input dimensions to 0, since we only want to infer one single image. Now, it could be more if we wanted to infer more images, but right for now, we could set it to 0. Just like that. And now we have this image, and we can return it just like that. And we'll return it as a float value, and we can add any other kind of preprocessing that we want. The last step, step 3, is inference or prediction, whatever you want to call it. And that's just 2 lines of code. Take that pre-processed source and then make a prediction based on that, right? So just like that, we take that processed input, we feed it into the model, and boom, it outputs a prediction just like that. And the result is going to be a dictionary containing probabilities of every class that it predicts, if it's a classification model. And the class prediction is the one with the highest probability, right? That's the highest likelihood. So there are some great resources to learn more about Tensorflow.js. Obviously, the Tensorflow.js docs are incredible. I've got a video on it. This is a video. And also Daniel Schiffman, who's a YouTuber. Definitely check out his series on Tensorflow.js. I have a link to it right here. Check it out. So that's it for a little bit of a primer on Tensorflow.js. Now I want to talk about pose estimation, the problem we talked about at the very beginning. So if you've ever used the Microsoft Connect, right, or if you've ever been in a demo like that, you just show up in front of it and all of a sudden it maps your skeleton, right? So there's this like skeleton layer on top of your real body, and wherever you move, it's going to move. So what it's done is it's estimated your pose, the pose of your human body, where your arms are, and not just where your arms and your hands are and your feet are, but where they are in relation to each other. And that's what that line is that's connecting those dots. So if we think about the pose estimation problem, it's not a generic classification problem. We're not trying to detect that, hey, this is an arm, or hey, this is a foot. What we're trying to do is build this pose based on those things. So if we think about it intuitively, this is an image, and we are trying to process an image using learning technology. We want to learn about what a pose looks like, and once we learn what a human pose looks like, we can make an inference or prediction on a novel pose like myself, and instantly it'll know, right? So how do we do that? Well, if we think about it, right, we're using our intuition about neural networks, images, okay, immediately convolutional networks springs to mind, right? So we'll use a convolutional network to do this. The next question is, well, how do we do that? And let me get to that in a second, but I also want to say that this idea of pose estimation has many use cases, right? So if we think about augmented reality, right? If you're in the game world, it should know where your hands and feet and, even head are in order to make objects in the environment move appropriately. For animation as well, right? So, Gollum, all these like Lord of the Rings films where they have all the balls on the person and they're dressed in this green or black suit and they're crawling and they're doing things. And then later on, you see the animated version of that, right? So normally this is the kind of thing that's going to democratize animation. Big Hollywood studios that have huge budgets have been the only people able to do this. But with this, anybody can make these pose estimations of people very easily. Okay, so there's that. And lastly, fitness, right? Fitness tracking to see, if you're doing the right form, if it's, like whatever it is, it can do that as well. So, right. So back to my, explanation of how it works. We should use a convolutional network. That much we know. Now, the second part is to think about the way it's actually going to learn about a pose. Before inference, how is it going to learn what a pose looks like? So if we think about it, what's the easiest way? The easiest way is to think about this as a supervised learning problem. So if we Google pose estimation supervised, we've got a handful of papers that do this. And some of the more popular papers are using supervised learning. But there's also, if we Google search unsupervised, there are unsupervised methods as well to do this. So this would involve clustering of some sort. But for the supervised part, if we think about it very intuitively, what it's going to do, and now this looks very similar to, if you recall my YOLO object detection video, just search YOLO Siraj, first link on YouTube. If you look at this picture, it looks very similar to YOLO because it's grouping all of these body parts into different classes. And then once it's found the one that is most encompassing of a given body part, we can then say that this is the right ankle or whatever. So at first, it seems like a classification problem because we have to identify that this is indeed a foot. We don't have to tell the user that, but we have to identify that and then identify other body parts. So if we think about it as a supervised learning problem, we could give it labeled images of body parts, just like, a hand or an arm and different variations, like all those variations. And what it would do separately, or the same model, it would first learn the mapping between arm and arm image, the mapping between hand and hand image, the mapping between, you see what I'm saying? So it would learn the mapping between all of those body parts. And then once it's learned all of those mappings, then once it sees a person, it's going to know, okay, that's everything that I've learned. And it can label them with a point marker. And once it's got that point marker, then we can connect the dot, literally connect the dots. And that's just, that's not even machine learning. Just connecting the dots, that's just, D3 or some kind of visualization tool. But then we have the pose. So that's the supervised way of doing it, right? So, but then the unsupervised way would be different. Now, that's not as popular, but that is a way to do that. So I've got this great video on that called, it's using the Will Ferrell image. It's YOLO again, YOLO object detection. Basically, it's looking for directions. So it considers all of these pixels as gradients. And it's looking for directions that these gradients of light are moving. So it first converts the image to black and white, and it sees where the direction all these gradients are moving. And so if the direction for, say, a nose is like this, it's likely a nose. Or it's likely some body part that sticks out because it has a point, like an elbow or a nose or a shoulder, or fingertips, etc., or a head as it just stands out in terms of lighting. It's using the clustering of lighting to identify body parts. And that's what unsupervised learning is all about, clustering, right? That's not as robust as mainstream, I guess you could say, in the ML community as the supervised methods, which are easier, but it's still it's a very useful thing to think about as well. So PoseNet is the model that we are training with, right? So PoseNet is the model we're training with. It was trained in pure TensorFlow. We can port it to Tensorflow.js. And we can think about the problem of pose estimation as two problems, actually. There's the problem of single person pose estimation, and then there's multiple pose estimation, right? So if you have one person in an image versus several people in an image, wildly different context. So single pose estimation is actually faster because it's only one person, but multiple person is slower, but then you can detect, 100 or whatever people. And interestingly, multiple pose estimation, it doesn't matter how many people there are. The complexity is n. It's not like n squared or n cubed or something. The more people, it just gets linearly more complex, which is very interesting. But anyway, the way this works is let's talk about PoseNet. So first, an input RGB image is fed into this convolutional network, PoseNet, and then either a single pose or multi-pose decoding algorithm is used to detect poses. And then the output is a pose. Now this pose is going to contain a list of key points and an instance level confidence score for each detected person, right? So here's a key point for this person's elbow and this person's arm, et cetera, and then we can map those on using some visualization tool, right? So these are just coordinates on an image plane. Right, so this guy, he's got 17 pose key points, and we can map those on. And what it's going to do is it's going to give us all of those coordinates. It's our job to then map those onto the image so we can view them. Same for this girl as well. So this single pose estimation model, it requires a couple of inputs, right? So a couple of parameters. How much to scale the image, whether or not to flip it horizontally, what is that image, what's the pose, and then the outputs are going to be the pose itself, the key points, and then the model, whatever, logging data that you add in as well. But we can tune the level of quality we want by tuning the stride parameter, right? So we can tune how accurate it is for one person by tuning this stride parameter from 8, 16 up to 32 and then back down again. And there's a trade-off here. So one is faster in terms of processing and one is slower. But if it's faster, it has lower accuracy, but if it's slower, it has higher accuracy. When PoseNet processes an image, it is in fact returning a heat map along with offset vectors that can be decoded to find high confidence areas in the image that correspond to those key points. Now this is what I was talking about when I referenced the YOLO object detection video, right? So it's looking for, notice his nodes. There's a gradient of light in a direction that's moving towards the center of his nodes, and that can be considered a heat map of key points. So when it comes to, so that's kind of the general way that single person pose estimation works. Multiple person pose estimation is similar, but it's slower. It has very similar inputs, the image, scaling factor, whether or not to flip it horizontally, the stride, and then there's the additional one, maximum pose detections, right? So how many people, the high level threshold do you want to detect in terms of their poses? And the output is going to be all of their poses. Now, when it comes to even multiple pose detection, there's more to that algorithm, but notice how we can code it just like this. This 10-line of code snippet shows us how to do multiple pose estimation very easily. All we literally say is call that function with those inputs, and it's going to give us all of those poses as an output, all of those coordinates, okay? So what I want to do now is code a little bit to show you just how simple it is. Okay, so we can do this in HTML very easily. I'm going to do that, in fact, right now. Just tune this to HTML. Boom. Okay, so using HTML, we can code it. We can create any simple HTML file in our text editor and then look at it in our browser easily. But you might be thinking, wait a second, how are we supposed to load Tensorflow.js if we don't have to install any scripts? Well, we can call it directly by saying the source of this script is going to be online. So it's unpacking that data from the interwebs, and it's saying that we want that data. Okay. All right. So that's us loading Tensorflow.js. Now we'll load PoseNet. So for loading PoseNet, we'll say, well, we have our library that we want to use. Let's use the model that we want to use, and that's called PoseNet. So it's got a source equals equals da 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 script, right? Just like that. Done. End it. Yeah, cool. Right, so there's that. I'll end the head tag just like that, and that's it for our header. Now we can code this thing. So let's say, like, what do we want to run this on? I'll say, well, it's going to be this cat image that I have locally. So I wanted to detect the pose of the cat, right? So this could be a human, it could be whatever it is, but I'll just say cat. And that's going to be it for the body. And then now that I've got that, I can go ahead and place my code inside of this script tag. So now comes the Tensorflow.js. I've imported the library, I've imported the model, and now I can actually code this thing. So I'm going to say, well, here are my inputs. The scale factor will be 0.5. The output stride will be 16. Whether or not to flip it horizontally, well, let's not do that this time. And the image itself is going to be an element that I pull from the DOM using getElementById. It's going to be called cat. And then I'll load in PoseNet, just like that. PoseNet.load, and then I'm going to say, let's return the net, estimate a single pose using that image element, the scaling factor flipped horizontal, and then output stride, and then it's going to print out in the console that pose. Okay, so let's see what this looks like. I'm going to say open tf.html in the browser, inspect in the console. Here are my key points right here, right? All my left eye, left ear. This I did without installing anything. This is happening locally. I just have a single image. It made those predictions. Here's where everything is. Check out the links in the video description. I've got links for you that's going to show you how to do this in the browser, code-wise, and other learning resources. Hey, you made it to the end of the video. If you want to be an AI god, hit the subscribe button. For now, I've got to make a pose. So thanks for watching.